Hello everybody. In this video, I'm going to talk a bit about universally quantified statements, explain what that means. We'll take a look at a couple examples of universally quantified statements. We'll see several different ways that these can be expressed. And we'll also look at universally quantified statements that involve implications and look at how these can be expressed. And we'll look at an example of that as well. So first off, what's a universally quantified statement? What is a universal quantifier? So universal quantifier is, well, let me start with this. In any case, we have an open sentence. So let R of X be an open sentence over some domain S. Now, as we know, R of X isn't true or false, right? We have to plug things in. So like R of 5, for instance, if 5 is an element of S, could be true or false, but not both. But R of X itself is an open sentence, right? But we can take this open sentence and turn it into a statement by making some kind of statement about the open sentence itself. In particular, with the universal quantifier, we're making the statement that R of X is true for every X in the set S. Then the statement for all X in S, R of X is a statement. So right, I'm not saying R of X is true. I'm saying that R of X is true for every element of S, right? So that's a statement. This is true when every element of S gives me a true statement for R of X, and it's false if there's some element of S that does not make R of X true. This could be expressed in a couple different ways. We could say for every X in S, R of X, that's another way to say it. We could also say let X be an S, then R of X is another way to say this. These are three equivalent ways to say it. For all X in S, or let X be an S, or for every X in S, or we could also say for each X in S, R of X. These are all different ways of saying the same thing, that every element of S gives me a true statement for R of X. Now, symbolically, this looks like for all. This is the statement for all, or this stands for all X in S. Oops, I don't want that. A comma. For all X in S, R of X. So this symbol here, this guy, means either for all or for every or for each. These are all equivalent ways of saying it. Is a universally quantified statement. Right? It's universally, because I'm saying that it's true for every element of S. So if that's my universe, it's true for all of those. This is why we call it a universally quantified statement. So let's go ahead and look at an example of this. I'll look at example 3.1 from the text. Here we have the open sentence R of n squared minus n is even. Now right now this is just an open sentence. It's not quantified yet. And I'll say here where n is an integer, or n is in the integers. That's my domain of the open sentence. Now I can take this open sentence then and make a statement about it in relation to this set, its domain. So then the statement, I'll just say then, for all n in Z, R of n is a universally quantified statement. So what am I saying by this? I'm saying for every, or for each, or for all, for every integer n squared minus n is even. Now this now could be either true or false, right? Now this is a statement. If every integer n, if it's the case that n squared minus n is even, no matter what integer n I give you, then this would be true. If there's some n for which this is false, then the universally quantified statement is false. So that's the idea. And really in this section of the text, we really are just getting the hang of expressing things as universally quantified statement. We're not yet to determining whether a universally quantified statement is true or false. We'll get there in the next section where we talk about proofs. Let's go ahead and look at one more example of these, and then we'll talk about implications. So example 3.3, we have the open sentence R of n, 5n plus 3 is even. In this case, n is an odd integer. Then we'll say let S be the set of odd integers. And say I want to make the statement, I want to claim that any odd integer, for any odd integer n, 5n plus 3 is even. So I could write that as for all n in S, R of n, which of course is saying that for every odd integer, for every odd integer n, for every odd integer n, 5n plus 3 is even. Or of course we could say for each, for all odd integers n, 5n plus 3 is even. Any of those are fine. And I'll introduce another way to think about this, that in some sense a universally quantified statement can be thought of as an implication. So we could also say if n is an odd integer, then 5n plus 3 is odd. And for our purposes, we'll consider this as a universally quantified statement, as an alternative way to express this universally quantified statement above. And in general, this is true that if I want to make a statement like for all x in S, R of x, something like this, I can express this as if x is in S, then R of x is a perfectly fine way to express these. So we'll see this used later. All right. Now I want to get implications into the mix a little bit, because oftentimes we'll want to prove a statement like where R of x is an implication. Sorry, I don't want equals there, I want dots. So often we have R of x is actually an implication. And so we'll want to, let's say, over domain S. What does a universally quantified statement look like here? Well, it look like for all x in S, P of x implies Q of x. So how could I write this in words? Well, I could say for every x in S, P of x implies Q of x, or I could say for all or for each. But there's a couple other ways when this is an implication that you'll see this expressed. For instance, we could also say let x be in S if P of x, then Q of x. So this idea of saying let x be in S, this is the same thing as giving a universally quantified statement. So this is also universally quantified. So when you see that word let something be an element of something else, of some other set, that's a hint that this is really a universally quantified statement, and it means this thing above. For every x in S, P of x implies Q of x. So let's look at an example of this. This is example 3.4 from the text. And this is true above if I have a biconditional here, right? I could say let x be in S, then P of x if and only if Q of x, right? I could also do something like that. So biconditionals are okay in here too, and we could use the same way to express this. So example 3.4, here we have two open sentences. 5n squared minus 2 is odd. And q of n, which is n, is odd. And here, what are we going to let n, where n is an integer? Then I can say, for all n in the integers, p of n implies q of n. So this is a universally quantified statement. Right? I'm saying that for every integer, that if p of n is true, then q of n must follow. That's what this statement is saying. And this can be expressed in a couple of different ways, right? I could say for every even integer, or sorry, for every integer n, 5n squared minus 2 is odd. Or maybe I'll say if 5n squared minus 2 is odd, then n is also odd. That's one way to say it. I could also say for all or for each here. I could also say let x or let n be an integer. If 5n squared minus 2 is odd, then n is odd. These are all perfectly acceptable ways to write this. Okay, that's it for this video. We're going to see another kind of quantified statement. So this is universally quantified. In the next video, we'll see what's called an existentially quantified statement, which is a little bit different than this one. All right, see you there.